Welcome to Room A603, located right here on Level 6 of the School of Industrial Technology. Today, we're stepping inside to put this classroom's climate to the ultimate test. First impressions? It feels okay in here, but check out the real MVP up there. A centralized air conditioning unit installed right in the middle of the ceiling, blasting out that sweet cold air. But how do we actually track this? Coming to action, the Raspberry Pi 02W, we've hooked it up headlessly via command prompt to this HDT11 sensor to monitor live temperature and relative humidity data. And to keep that cool AC air locked in, these heavy curtains completely block out the intense external heat from messing with our zone. Let's check out the setup and see how we got it all running.
This is the video of our first attempting to set up the physical sensors for our project. But this setup wasn't a success, so we try another setup. I will explain it next. This is the new setup of our sensor. First, we're looking at the sensor breakout board. It contains 3 pins from the top to the bottom, where S is indicates the signal for data, and the middle pin is for power. Last one, negative pin for ground. From the sensor breakout board, we connect the jumper from the power pin to the red rail and the negative pin for ground to the blue rail. From the other side, the Raspberry Pi board, we connect the pin 1 to the red rail and the pin 7 to the blue rail. For the last 2 jumpers that connected the ground pin from the sensor breakout board and the Pi battery board, these 2 directly connect to the breadboard. So next part we'll continue to the coding part. Thank you.
Alright, let's get this project moving. Opening out the command prompt and SSH right into our Raspberry Pi. Just log in, hit enter and type your password. We're running a quick system update, installing Pi so we can grab Python package and then downloading the official library specifically for our DHT11 sensor. Now we're running a test script and we are immediately grabbed by a wolf send error shouting sensor not fine, check wiring. So it's time to figure out what went wrong. We're pushing the old library, swapping in a different driver package, and double checking that our script is looking at the correct data pin. Clean data start rolling down the terminal. We're getting a perfect local reading of temperature and humidity. We rewrite the logic drop in our unique ThinkSpeed API key. When we try to install our web library, the Pi shows environmental error. So we found that it's due to the bug. We changed from board 17 to board 4.
This program reads temperature and humidity from a DHT11 sensor and uploads the data to ThinkSpeed. Data is uploaded continuously.
The data is then transmitted to ThinkSpeak using the right API key, which enables communication between the device and the cloud platform. Once the upload is successful, the readings are stored and displayed as graphs on ThinkSpeak. From the graph, we can monitor the changes in temperature and humidity over time, allowing the data to be analyzed in real time.
Now I'm going to demonstrate data visualization on the ThinkSync platform. To begin with, I create a new ThinkSync channel and complete its basic information before saving it. I set the API key provided by this channel. This key is inserted into our Python code so that sensor data can be uploaded to the cloud channel correctly.
Once the DHT11 sensor collects real-time temperature and humidity data via Raspberry Pi 02W, this data will be transmitted to ThinkSpeak automatically. The platform voice roll data into visual charts instantly. Moreover, I can edit chart labels manually to make different parameters. These visual graphs help us observe real-time data tenders to invalid classroom environment conditions.
Hello there, my name is Ashika, and I will be talking about the findings and discussion. Looking closely at the temperature graph on the screen, we can observe a distinct environmental trend over our 11-minute observation window. At entry 1, the classroom baseline temperature started at 27.6 degrees Celsius. Over the course of 32 sequential updates, the temperature steadily and uniformly dropped down to a stable 26.7 degrees Celsius. This physical decline in temperature correlates perfectly with our real-world observations of the classroom's occupant load. At first, there were quite a few people inside room A603, which initially kept the baseline temperature higher due to body heat. However, as people slowly started to leave the room, the human thermal load decreased. Because our curtain-covered windows successfully blocked out direct solar radiation and heat reflection, the centralized ceiling AC was able to easily overcome the remaining thermal load, lowering and stabilizing the room's temperature as the crowd thinned out. Simultaneously, our humidity graph shows that relative humidity started at 48% and experienced a slight initial drop before tightly stabilizing between 42% and 43%. This indicates that the air conditioning system was effectively dehumidifying the air as it cooled down the room. Now, why does this actually matter? Maintaining an optimal classroom temperature is absolutely critical for enhancing student learning. When a classroom is too hot, cognitive fatigue sets in, causing students to lose focus, feel drowsy, and struggle with information retention. By utilizing our IoT system to monitor and ensure room A603 stays at a comfortable, stable climate, such as this optimized 26.7 degrees Celsius and 42% humidity level, we can scientifically guarantee an environment that keeps students sharp, engaged, and perform at their academic best during long-term lectures. Our Raspberry Pi IoT architecture successfully captured, uploaded, and proved this environmental dynamics seamlessly. That's all for my part. Thank you.